Hello, everyone. Today we're going to be graphing square root functions. So before we get going, you guys already know what I'm going to say. Pause your video, and if you could try the review problem at the top of the page, that would be awesome. And go. All right, answers are up for this one. All you had to recognize was that at the end where it says if g of 4 equals 31, you just have to realize that that right there in a way is a point. It's saying when x is 4, y is 31. So that's information that you can use. Because remember, g of x, that just stands for y. And if you know x and y, you can use that to find the constant a that's missing in this case. So all you had to do is plug in x is 4, plug in y is 31, and solve for a, and you get your final answer of a equals 11. So C was the final answer on this one. Now, before we get into going what we're doing today, you might want to grab out your graphing calculator if you have not already, if you want to try them along with me in the video for today. But today we're going to be graphing square root functions. Now, just like most other graphing units at this point, most of what you can do today is really going to be done mostly in the calculator. But let's start off with our first square root function, which just like all other functions that we really work with, this is what we call the parent function. Ooh, sorry. The parent function, which in your own words, I don't know how you guys would describe it, but when I think about the parent function, I always think about the parent function as kind of like the most basic shape of any graph. Like the most basic quadratic function, that was just our y equals x squared function. It's kind of like the simplest one out there. And if you actually go to your graphing calculator, I am going to share that with you guys now. So if you guys are in your graphing calculator and you go to the y equals page, we're going to type in our function. It's y equals the square root of, which on the graphing calculator, square root is actually right above the x squared button on the left-hand side in blue. So if we hit the second button and then I hit the x squared key, that is how you can get your square root symbol. And to get the x in here, that's just the button to the right of the alpha button. And I'm going to click on that one right there. It has all like the little xt, there's a little theta in there, and if you hit it though, an x will just pop up. And if we hit graph, we can kind of see what this looks like. Square root functions are kind of my favorite. They have this kind of like shooting star format to them, where they kind of like start at a point and then they shoot off forever in one direction. So typically how we'll start most square root functions is if we go second graph and we go into the table. You guys are going to notice that there's a lot of things that cause an error. And that's because you'll probably start to see where it happens. If I have 0 and then -1 and beyond, and everything before -1 is an error, what that means is that all of those are not in its domain. And that's because you can't take the square root of a negative number. Square roots, basically whatever number is underneath, you're saying that there is a number in the universe that's, when you square it, gives you that number. And negative numbers, that's not true. Because no matter what number you pick in the world, any number that you square is always going to be positive. So none of these negative answers are possible, except for until you get to 0. 0 is something that works. What squared gives you 0? Well, 0 times 0. So you guys can start to kind of figure that out. But all of these pieces is kind of culminates in the fact that usually what we'll do is we'll graph kind of like the first 3 that fit. So everything up until -1 was an error. If you guys look on your notes, which I'm going to flip back to that actually. If you guys look at your notes, you notice that I provided you with a little table. So that's actually what we're going to filter in. I'm not going to start at -1 because that was obviously undefined. But starting at 0, 1, and 2, those are kind of like the nicest points that we can pick and plug in. So 0 was at 0, 1, 1. I'm just filling these in from the table from the calculator. And coincidentally, those are usually the 3 points that I'm going to look for you to put on the graph. So 0, 0, 1, 1, and over to up 1.4. It's not going to be an exact science because there are going to be some decimals on this one. But the gist is that once you go through, we're going to draw our line off to the distance and it's going to have an arrow on the end. Now, just like all parent functions, there is technically a parent function, like an overall basic function for all square roots. And it looks a little bit something like this. That's y equals, ooh, caught my sleeve, equals a square root of x plus h minus h, whoopsies, x minus h plus k. So it's kind of along the same lines of when we graph rational functions. The number inside is kind of like the point, and then combined with the number outside, those kind of form your starting point. It's not really like a vertex per se, but here that makes sense in the sense that there was nothing out in front on the inside. It was just x plus 0, and our graph started at 0, 0. The reason why that also is really helpful, though, is because it also notates our domain and range for us in a way. Because here, until everything up until 0 is not something that I'm allowed to plug in. You can't get any negative x values. So once we go through and start to figure out what our domain is, it's a little easier to kind of look at the graph. Here, all my x values, it starts at 0 and it goes forever to the right. So really it's all x values that are greater than 0. And that is going to be my domain. It's all values of x that are greater than or equal to 0. Range is kind of the same way. Range, it's all about the y's. So the lowest point on my graph is this point right here. And all of my y values go up from here. So that means all my y values, it's going to be y is greater than or equal to 0. Now, I'm going to cross off compared to the parent because this is the parent, so we're not going to compare these two together. But in general, that becomes your overall function. Now, once we start changing things, then we can answer that compared to the parent. Then we can start to say, am I having a vertical shift? Is there going to be a reflection? All that fun stuff, which we will cover on example number 2. So in example number 2, you guys are going to notice that here there's a lot of fun things going on, but we're going to start as always by going to my graphing calculator and graphing it. So I'm going to share with you guys, let's go back to my graphing calculator and let's go back to the y equals function. So here I'm going to type in my function. So it's going to be -2 and then square root. So second x squared, and it's going to be x minus 3 on the inside. Now to get to the outside of it, you do have to press the right arrow once. You'll notice because it won't actually continue writing anything. Like if I keep going, it won't bring that square root over. If the square root keeps getting drawn over it, that means you didn't arrow out of the square root. So just press to the right once, and then you should really be good to go. Okay. But I'm now going to look at the graph. Let's see what this looks like. Now this one looks a little bit weird. Weirder, obviously, right? Hopefully, let's look at our table. Let's start to see kind of where that first point is. So all of these are errors. The first point that we see is 3, -4. So that's going to be the first point that I'm going to look for you guys to graph. And that means something a little more specific too. If we flip back to our notes packet, 1 second, there we go. So obviously that 3, -4, that again, it's not the vertex, but it does technically come from the equation. Opposite of what's inside, whatever's outside. It's not the vertex, it's just kind of like the starting point. And those are kind of your boundaries for most of the other things. Now, if you fill in the rest of that table, you guys can look at it if you was second table. You can look at actually at the table for this one or second graph. But it should have been 3, -4, 4, -6, and 5, -6.83. So those are the points that I would start by graphing. So we're going to go start by going right 3, down 4. Boom, plot my first point. The next one I go right 4, down 6. And there we got our next point. And then last but not least, 5, we go down 6.83, kind of somewhere in there, and draw our little shooting star. Oh God, I missed that one, but you guys get the gist. Now, this one we have to be a little bit careful when I choose my domain and my range. Because my domain, remember, that's my x's. So my x's start here and go forever to the right. So that value is going to be at x equals 3. So for us, we're going to be at x is greater than or equal to 3 is going to be my domain. My range, on the other hand, here, because we have that negative in front, that is a specific change from the parent. But the reason why it changes things the most is because if I look at my y's, this is the first point that we graph, and all of my y values, the graph goes down. So I never go above -4 as my answer. So here, all my y values have to be less than or equal to -4. So it's all about, is it above or is it below? If it's below, it's going to be your less than or equal to symbol. And if it's above, that's going to be your greater than or equal to symbol. Now, when it comes to the comparisons, remember, we do have a couple different types. We have kind of like our 2 shifts, in which case we actually have both of these, a number on the inside and a number on the end. That actually lets you know those are where your 2 shifts would pop up. So since there isn't a 0 in one of those places, that means I'm shifting right 3 and down 4. So in terms of transformations, we definitely have both shifts. We have a vertical and a horizontal shift. Because my starting point moves from 0, 0, right 3, and down 4. Now there are a couple other types. The next one is called, let's go with stretch or compression. And that's always something that you can tell from the number that's in front. Remember, the A value, just like quadratics, the A value tells you if you're stretched. If that number in front is more than 1, we basically ignore the sign for just a minute. But if that A value is greater than 1, that's our stretch. If that A value is a fraction of some sort that's less than 1, then that becomes your compression. So in this graph, since we have a 2 in front, again, we ignore the negative. The negative is something different. But since we have a number larger than 1 in front, that just means that we have a stretch. Basically just means my shooting star gets a little bit taller. And last but not least, with that negative in front, maybe you remember what this is, but that is a reflection. A reflection basically just means your shooting star is going to go kind of down and to the right instead of up and to the right, like the parent function. Okay. So if your graph kind of ever goes the opposite direction, then you know that that graph is going to have a reflection to it. Okay. So what I want you guys to do, I want you guys to pause your video and I want you guys to try example number 3. All right, answers are up. For this particular one, your graph obviously should have looked something like this, where you had your table 6, 2, 7, 3, and 8, 3.41. Graphing wise, I am going to look for you guys to graph those 3 specific points. Now, for your domain and your range, that one is always based off of the front one, or the first point that you're able to graph. So since my x values, obviously we start at that first point and we go to the right. So for my x values, it's going to be x is greater than or equal to 6. And for my y's, this one's just a little bit different because we still focus on that first point, but we focus on up or down. From that point, my graph really kind of goes up and to the right. So it's everything that's going to be greater than or equal to 2 in this case. Now for this one in terms of comparing to the parent, there really only had 2 transformations. It had a vertical shift and a horizontal shift because we had numbers inside with my x and out on the end. The reflection and your 2 types of stretch or compression, that would all be if you had a number other than 1 out in the front, which we don't. Now, you do if you look down a little bit actually to the next section. It says analyze square root functions. Here, I'm going to basically do kind of what we did above, and you're just going to do it basically without graphing. I know for a fact, like for example, this one, if I look at my starting point, opposite of what's inside, comma, whatever's outside, that is kind of the first point that you're able to graph. And because my graph is not reflected, then I'm just greater than both of those values. It's going to be everything to the right of 7 is going to be in there. So our domain is going to be x is greater than or equal to 7. My range, since it's not a negative and my graph isn't flipping down, then my range is just y is going to be greater than or equal to 3. Now, comparison to the parents, what you just found are your first two. Because you have a number of 7 and 3, both h and k are a number, that means we have both a vertical and a horizontal shift. We don't have a reflection because there's no negative in front, but we do have another one because there's a number other than 1 in front, and because it's a number larger than 1. This right here tells us that we also are going to have a stretch. Whoa, iPad's freaking out, guys. But this is your domain and your range, and these are your comparisons to the parent. So what I want you guys to do, I know we didn't do one like number 6 first, but I want you guys right now to try number 5 on your own and try number 6 on your own. Go ahead now. All right, answer for number 5 is up for this one. Sorry guys, excuse me. So for this one, because if I look at my starting point, opposite of what's inside, comma, what's outside, in this case, it's just a matter of determining if it's greater than or less than those values. The nice thing is that for your x values, it's always going to be greater. The x is always going to be greater than whatever is this here because your shooting star, no matter what, always kind of shoots off to the right. The range, on the other hand, this is the one that it could flip. If you don't have a reflection in front, then it's always greater than. If you have a reflection, it just means your graph is going to kind of go down and to the right, in which case it's going to be less than whatever value is on the end. So that's why here your domain is x is greater than or equal to 3, and your range is y is less than or equal to 2. Now, if you need a picture of this graph to be able to tell, just because I didn't make you graph it doesn't mean you can't use your calculator. If you want to graph this and kind of see which direction it goes and then determine your domain and your range, that's totally fine. But out of all the transformations, this one had almost all of them. You have both a vertical and horizontal shift because you have a starting point other than at 0, 0. We do have that reflection because the sign in front of your A value is negative. So that's what makes your graph flip upside down basically. And the last one that we actually have a compression on this one because the number in front, that 2/3, obviously is a fraction that is less than 1. All right. Now, number 6, I had you guys try just for the fun of this. Now, for these, a lot of times we can't always determine our A value from this, but I do know for a fact that my equation right now starts at -4, 0. So if we're working kind of our way back, if this is my base function. Ooh, wow, that was awful. One sec. X minus h, what is it, plus k? Then the h and the k, these result from, or kind of come from, the place in the equation where h and k are. So remember, just when we plug things back in, we know for a fact that h, it's always opposite when you plug it back in. So because it's a -4, I'm going to plug in a +4. And I could put a +0 on the end. I'm not going to put that in there. And typically for this one, usually you can always tell your A value is 1 because we go over 1 and up 1. That only works for the first set of points, but for this one, that just lets me know my A value on this one is going to be 1. And there is our function. All right. I do have a couple problems down low if you want to give these a shot, but if not, if you're feeling good, then you guys can move on and you can start working on the homework for today.